stable part.
Yeah, maybe you'll get.
All right, I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to guide our steps today. Help us to just understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me start. First of all, I should, if you please pass your missions to the aisle, so I can pick them up. Thank you. What? I do not have a stapler, so sorry, I do not have a stapler. That is true. Please pass them to the aisle so I can collect them. Thank you. Thank you, thank you.
I put my name on it. I want to make sure.
Thank you.
This one needs to.
Thank you. Thank you. All right. Thank you.
Will we get these back after you grade them?
Yeah.
Okay, cool.
But as a general point of order, the smart thing to do would be to, like, I would scan these if I were you. You know, it takes like just a few minutes if you scan them. And, well, especially the one that's right before the test. Like, there's no way I'll get the mission graded before the test, right? The one that's right before the test. So you should really scan it so you can compare to the solution to the mission, right? So unfortunately, my solution is at home with my backpack, which is why the camera is rubber banded to the thing, if you look, because I'm borrowing that one from IT. And so, yeah, sorry about that. But I will have the mission solution posted like early tomorrow, hopefully. I have solved them. But, okay, so let's talk about a problem just to get started today. This is the famous monkey shooting problem. So the problem, here's a problem. Is in the figure below, what's the minimum initial speed of the dart if it is to hit the monkey right before the monkey hits the ground, which is 10.2 meters below the initial position of the monkey? If x is 40 meters and h is 9 meters, and ignore any effects due to air resistance. All right. So the answer is in the box because this is a printout of the key from like a WebAssign years ago. All right. So and this that we're looking at right now is posted on the website, on the course website. It's called like monkey shooting or something. You can find it there. If you have any trouble finding this, just email me. I'll send you the link. Okay? Yeah. Okay, so here's the basic idea to solve this problem. Is what you want to have happen is you want the to do the let's see here. So I say intuitive leap. The minimum velocity is the one for which you get the monkey right before it hits the ground, right? So that's the question. What's the minimum initial speed of the dart if you want to shoot the monkey? All right. So if you think about that, if you had a super fast gun, you could just shoot the monkey. So like, well, man, I was going to go back and get my laser, but oh well, ran out of time. So if you shot the monkey up here, that would not be the minimum velocity, right? Because you could shoot it slower and hit the monkey down here, right? So that's the first sort of intuitive leap here, is to say, well, I want to hit it right when just as it gets to the ground, right? So the time for the monkey to drop, you got 0 that's the time when it's just before it hits the ground, right? You're at y equal to 0. Now you're firing your dart from that initial height, y sub 0. Let's see here. So y sub 0 minus 1/2 gt squared. That's the monkey. This is for the monkey, right? So the initial height of the monkey is 10.2 meters. It's not, the monkey's just dropping, right? It's not like leaping to the ground. So its initial y velocity is 0. So that's why there's not like a v0 yt term here, right? It's just y0 minus 1/2 gt squared. And that's equal to 0. So I solve for t. I get 2y0 over g. On the other hand, the position of the dart is given by x equals v0 cosine theta times t, right? So this is projectile motion, the constant acceleration in the x direction, right? So there's no like 1/2 acceleration times squared term for this formula, right? It's just the velocity times the time. The x velocity is v0 cosine theta, right? And great. So we've got t is x over v0 cosine theta, and that's equal to the square root of 2y0 over g. And well, I say since v0 and theta are unknown, I need something else, right? This is not enough yet because there's two things that I don't know, right? I don't know the theta and I don't know the, let's see here. Yeah, I don't know theta and I also don't know v0, right? So I say I need another equation. What else can I do? Well, I can consider the equation for the vertical position of the dart, which would be given by this. 0 is y0 minus h plus v0 sine theta t. So this is the initial height of the dart. And let's see here. H, I think, is the... I've lost track of what h was. My bad. Sure, I set it up there. I've just lost track of it. What was h?
The initial position of the monkey.
The initial height of the monkey? Well, it's y0 then.
Why is there the initial distance, like change in distance?
I said h equals 9. Let's see here. The ground is 10.2 meters below the initial position of the monkey. H is 9 meters. That's a really convoluted way of saying that you're shooting the dart from 1.2 meters above the ground. Okay, that's what it's saying. All right. So like it's in the picture. You're shooting the dart from 1.2 meters. So like 1.2 meters plus 9 meters gives you the 10.2 total where the monkey starts above the ground. That's the meaning of the H here, okay? So the initial position of the dart is y0 minus, H is 9 meters. I'm an idiot. So H is not the 1.2, H is the 9. This is the initial height of the dart, okay, this is 1.2. And we have v0 sine theta. We don't know v0, we don't know theta, right? But this does solve to give us h is equal to v0 sine theta times t. So I have t is equal to this and also to that, which tells me that the tangent theta is h over x, which means then that theta is inverse tangent of h over x. Both h and x are given. And so we get 12.68 degrees. And then I can go back and put it into the other formula for v sub 0, and out pops this. So there's a lot going on in this problem, but I think it's worth looking at and seeing how the different kinematic equations are used together to solve a kind of interesting problem. Yeah. So yeah, there's that. Now let's look at an easier problem. One more here. So this one I haven't posted yet, but I'll post this for you guys. So there are other interesting problems in lecture 6, and I decided what I'm going to do, just so we're not hurried so much in here, is I'm just going to make like a small supplemental video where I talk through the other examples in lecture 6 for you. So it shouldn't be a long video, but it takes me a long time to write those things out in here, and I want to leave more time for other things. So in the interest of you having me blathering on about projectile motion a little bit more, I'll make a small supplemental video. But let's talk about this one while we're here. So this one's pretty easy. You got a hot air balloon. It's drifting 20 meters per second that away, all right? And you drop a cat. from the hot air balloon. And then the question is, how far horizontally does the balloon travel before the cat hits the ground some 300 meters below? So you can decide, is this S, is it for softly lands or is it for splat? I mean, you go whichever way you want, all right? I mean, it's a cat, it's probably going to be fine. They're like evil and stuff, they survive. But, okay, so this problem is easier than the monkey shoot problem, right? Because it's not all, like the monkey shoot problem's complicated because you don't know the angle, you don't know the speed, you gotta somehow eliminate one for the other. It's just, that's a hard problem. This is not. So your initial velocity, oh man, well I'm gonna have to rescan this. This cannot stand. I will certainly lose some points on this. Oh, yes, I have written scalar equals vector. So that way you know I don't know what I'm doing, right? No, so sorry about that. I must have been distracted by something when I wrote that. But there should be a vector here. I will rescan this and put the vector on it before I post it for you guys, okay? Anyway, that's your initial velocity. The initial y velocity is 0 because it just drops, right? It just dropped. But it has an initial x velocity of 20 meters per second because the cat's initially with the balloon, right? Okay, so on the other hand, my equation for y is 300 meters. That's its initial position, minus 1/2 gt squared. There's no time term here, again, because the y velocity initially is 0, all right? And so I'm looking for the time the cat goes splat, which is when y equals to 0. And so I solve that, I get t sub splat is 2 times 300 meters divided by 9.8 meters per second squared square root. Notice the units make sense here, right? Meters divides by meters, they cancel out. You had a 1 over second squared, which gives you the square root of second squared, which is just giving you a second. That's good. And that works out to 7.825 seconds. And then to figure out how far you went over, well, the cat goes just as far over as the balloon, right? As it turns out, because they both have the same horizontal velocity of 20 meters per second, right? Until the cat meets its demise and until the balloon just keeps calmly, drifting over, having improved its state by no longer having a cat. But so you get 20 meters per second times the time sub splat, and when you multiply this times that, you get 156.5 meters. Yep.
When you drop the cat, it does have an x velocity, doesn't it?
Yeah, 20 meters per second.
So why are the balloon and the cat not right above each other?
They are right above each other at the end. My picture is got two different time frames. Like I could have drawn the balloon again above over there, but I didn't. Like there's time going on in the picture. The dot 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 says time 0, time splat. Yeah. This is always a debate. Do you want to draw a separate picture for separate times? Do you want to try to illustrate animation with like one freeze frames of different things in one picture? I mean, it's up to you. These kind of pictures are just organizing. They're like an organizing principle for our work. There's not like a right way and a wrong way to draw the picture, let's say. It's not art, right? So, although this is hung on a wall right now, so I think it's art, right? Now once I close this PDF, it's no longer art, but, all right. So past this, and I'll talk more about this in the video I'm about to make, I studied the asymmetric range problem. The asymmetric range problem is how far does something go over when your initial and final height are not the same. If you want to maximize the range, it's no longer 45 degrees. It's actually a kind of complicated story, which I will tell you in the posted video. All right, teaser for the posted video is done. Let us move on with our life. So, let's talk about frames of reference. So what I want to start, so what we're working our way towards today is the statement of Newton's laws. All right, so, oh, thanks, you already fixed it for me. Awesome. Oh man, this camera is Oh, that's unfortunate. See the rats. Yeah, it's fuzzy. I can't fix it either. See, on my camera, which is a little bit older, they have this manual focus thing. You can turn off the autofocus and put it on manual. I couldn't find the button on this one. Is it not fuzzy now that I'm here? Still fuzzy? Oh, all right. So if you're not here, sorry. If you're here, I'll try to like maintain focus. So if I like become fuzzified while I'm standing here, well, that would be very bad. I don't know what that would mean. Perhaps some sort of like directed energy weapon, maybe. I don't know, right? All right, so here's the deal. We take frames of reference for granted all the time, but suppose you've got like an XYZ coordinate system, right? And then suppose you have another coordinate system, right? Over here, and we need, just for the sake of discussion, let's put some bars on it, right? Z bar, X bar, Y bar, right? So suppose you have two different coordinate systems, one with respect to one origin, one with respect to another, right? Then it becomes interesting to compare these two different coordinate systems, right? So just to give this a label, we could call this the S coordinate system. Oops, excuse me, S coordinate system. And I could call this one the S bar coordinate system, right? So consider two coordinate systems. What do we mean by that? What is a coordinate system? I think you just kind of take it for granted, but like what that means experimentally is we set down an origin, right? And then we have some means of measuring like displacement in three orthogonal directions, right? Like the X direction, the Y direction, and the Z direction. How do you actually achieve that in practice? Is it complicated business, right? Like maybe you have rulers. You got to make sure those rulers are perpendicular, right? If you're going to make, genuine XY measurements, and then vertical too. We know all of this in some sense is approximate because the Earth is a sphere, well, an oblate spheroid. That's right. Said it. Statistically, there's a flat earther here somewhere. Well, anyway, I'll explain to you my views on the flat Earth more later, but let's see here. I personally believe in the cylindrical Earth, but no, okay, I digress. More on that later. Let's not get me started on that. So these two coordinate systems, right? Let's take for granted that we can set up such things, right? And then if you wanted to compare two coordinate systems, right? What we'd like to do is to describe the motion of some physical object with respect to one coordinate system and with respect to the other, right? So what's the one thing that kind of links the two coordinate systems is the position vector, let's say, right? That was supposed to be a line. Let me call this r sub naught. So this is going to be the position. The position of origin of S bar with respect to S. Right? And then let's suppose that we're thinking about a material object. Yeah? A mass, all right? An object at some point. And let me put that in the picture here. So for the sake of my artistry, I'll put it down here, right? M, a mass, an object. You can give it a name if you want. Do you guys want to give it a name? Let's call it Bob. All right, so Bob's down there. We can either measure the position of Bob with respect to the S coordinate system or with respect to the S bar coordinate system, right? So in a picture, that's just this. So here's my, let's say, position with respect to the S coordinate system, like that, right? And what would the position with respect to the Man, I've lost, I don't have any fresh markers in other colors at the moment. Maybe this purple's alive. I don't know, we'll see. And then you can measure the position of Bob, here we go, with respect to the S bar coordinate system. How are these related? Yep.
The position of origin plus the position of S bar is equal to the position of S.
So you say the position as measured in the S coordinate system is equal to the position of the origin of the barred system in the S system plus the position measured with respect to the S bar. This is what you said, right?
Yeah.
Which is, you can literally see from the tip to tail vector addition in my picture, right? The red vector plus the purple vector is the blue vector. It's just that, yeah? But here's the kicker. These are all functions of time. What does that mean? What can you do to functions of time? How about we differentiate them? Yeah? What happens when we take the derivative of the position? So we get dr sub s dt equals to dr sub naught dt plus dr sub s bar dt. But we have other names for these, right? What we're looking at is simply this: the velocity of Bob in the S system is equal to the velocity of the moving coordinate system, S bar, plus the velocity of Bob measured with respect to the moving coordinate system. So conceptually, and it doesn't have to be the case, but I usually think of this as moving. I think of the S bar coordinate system as a moving coordinate system. And I think of the S as a given fixed coordinate system. Now that begs a sort of philosophical question, is like, what on earth do you even mean? How do you find something motionless in the world in which we live? Right? What's not moving? You're like the flat earth, you moron. No, sorry. Okay. All right, sorry. I've spent too much time on YouTube, I admit it. Okay, so this is the velocity rule. The velocity addition rule is very simple. It says to find the velocity in the moving, in the fixed frame of reference, you take the velocity with which the frame of reference is, the moving frame is moving, and you add the velocity of the object with respect to that frame of reference. Just, let me give you an example of this, yeah? So, oh, actually, let's finish the math here. Finish the math. Differentiate one more time, what happens? Differentiate one more time, we get acceleration. Exactly. So we get dv dt with respect to the s is equal to dv naught dt. And this is just by linearity of the derivative, right? Which extends to vector derivatives, just the same, no big deal. In other words, the acceleration measured in the s system is equal to the acceleration of the origin of the moving system plus the acceleration of the S bar system, like that. Okay, so yeah, so it's a simple example. Not entirely simple, but let's make it a little bit simple. Well, excuse me, not that simple. What I'm going to do is I'm going to take a train. Oh man. I'm not sure I can draw this picture. I'm trying. So I want the train to follow this track in the XY plane. All right, so I've got this train. Train is traveling on the XY coordinate system, all right? In the XY plane like this. So train, you know, at, let's say 100 miles per hour. Meters per second, well, yeah, meters per second, fine. Well, that's moving. And And for the sake of me not going nuts, I'm going to just draw the train like that, okay? But then let me draw a picture like this. Here's the train, right? And on that train, Mr. Top Hat is there, right? So, 100 meters per second, like this. Don't question how Mr. Top Hat isn't blown off, just accept it. All right? There are walls, not drawn, all right? Walls, there you go. Here we go. We'll encase it in some kind of wall, all right? Mr. Top Hat throws a marker, right? Up like this. Okay? What's the velocity of the marker? So let's suppose that the S bar is co-moving with frame. Listen to me. Co-moving with train. So what would the what would the position of the marker be with respect to the train? So let me draw the picture of the marker in the train frame. It looks like this. Okay? Marker path. Right? Just so to illustrate what's going on, if I walk like this and I just do like this, right? The marker comes back to where I threw it as long as I keep walking at a constant rate, right? I tried. I did it the first time. So you try this. If you just toss a ball straight up and you walk at a constant rate, the ball comes back to your hand where you threw it from, right? So the position hasn't changed in the moving frame of reference, which moves with you. In other words, I can say that the position vector of the marker is just 0, 0, and then in the z direction, we've got its initial height plus its initial velocity times time minus 1/2 gt squared, right? That's the position of the marker moving with the train in the train coordinate system, right? And fine, so what's the velocity of the marker in the, I seem to be changing bar to a vector, S bar. It's just what? 0, 0, V naught minus GT, right? What would the velocity of the marker be on this hypothetical train in the fixed coordinate system? What's the velocity of the train if it's moving on this line right here, which I'm saying is at 45 degrees? So the velocity of the train, right, would be 100 meters per second times the unit vector in that direction, which would be what? Cosine, right, we just do cosine 45, sine 45. In other words, and 0, right, for the z. So what you got is essentially about 70.7 meters per second, 70.7 meters per second, 0. That's the velocity of the train with respect to the fixed coordinate system in which the train is traveling, right? What's the velocity of the marker with respect to the fixed coordinate system? So the velocity of the marker with respect to the s coordinate system would be the velocity of the train, right? Plus the velocity of the marker with respect to the train. The velocity of the marker with respect to the train is what I've also called, aka the S bar. And so anyway, long story short, here it is. 70.7 meters per second, 70.7 meters per second, and then you got your V naught minus GT. I guess you guys want to pick, what did we figure out the velocity of the ball was the other day? It's the same for a marker, right? If it just barely hits the roof, what do we figure out was? I can't remember. Was it 15? let's just say 15 meters per second. So 15 meters per second minus, 9.8 meters per second squared times t. And there you go. That's the velocity of the marker that's being thrown on a train, which is going at 45 degrees standard angle across the xy plane with a speed of 100 meters per second. Assuming the marker was thrown upwards with an initial velocity of 15 meters per second. So don't get lost in the details here. The point is that there's a simple rule. We take the velocity of the frame of reference plus the velocity measured with respect to that frame of reference to get the velocity with respect to the fixed frame. Does this make sense? All right, so do you guys know what do Newton's laws say? What are Newton's laws? Why do we need to talk about Newton's laws? I mean, what have we been talking about up till now? So take a second and think about everything I've told you up till now. I haven't said word one about a force, right? We've talked about position, we've talked about velocity, we've talked about acceleration, but we haven't talked about force yet, right? So I've told you that the marker drops with, drops at 9.8 meters per second squared, right? But I didn't explain why, did I? So can you guys tell me what Newton's laws say? Can you state them for me? Well, it's okay. I've got a phone. And as you know, Google is the authority on everything, at least until the federal government puts them straight. There's an antitrust thing going on right now. There's hope. Let's see here. Here it goes. According to the Google, the laws are, number 1, every object moves in a straight line unless acted upon by a force. So the first law. Objects move in straight line unless acted on by a force. Of course, it kind of begs the question, what's a force, right? 2, what's the second law? These are all Newton's laws, okay? The second law, according to Google, is the acceleration of an object. Hey, we know what that is. Acceleration of an object, like Bob, right, is directly proportional to the net force exerted. Net force, now we're starting